Ah. Okay, so people are still coming in. So okay, so yeah, it's my great pleasure today that Mark Ivan is giving a talk today in our colloquium. So let me say a few words. So Mark asked me to keep it short, but let me still say a few words. So Mark did his PhD at the University of Michigan at Ann Arbor with Anna Gilbert. And then he went for a postdoc to the University of Minnesota, and he did a second postdoc at Duke. And since then, he has been a faculty at Michigan State, where he's now an associate professor. So Mark's research interests revolve mostly, I think, around computational harmonic analysis. He has worked on compressed sensing, fast Fourier transform, and dimensionality reduction algorithms. And I think, okay, so Mark asked me to keep it short, so I will stop there, but just say one more thing. So I think maybe, which is interesting. So Mark, I think, so when the pandemic started, Mark started organizing the One World Mind seminar, which I think helped a lot of us getting through the pandemic. And I think Mark really has been maybe the leading force. So thank you, Mark, for that. And with that being said, yeah, I think the floor is yours.
Thanks for the great invitation to give a talk and for the great introduction. Yeah, I want to talk today about low distortion embeddings of submanifolds. And I will start off hopefully with something that's a little bit familiar to some of you at least. So let's look at what I'll call Johnson-Lindenstrauss embeddings of a subset of Euclidean space. So the sort of setting here is we have a finite subset, let's say, of Euclidean space with big D dimension, so really high dimensional subspace. And we're interested in matrices, which have a small number of rows that preserve all the pairwise distances or squared Euclidean distances, if you like, between all the points in S. So this is sort of the starting point, a bit of a review for what we're going to talk about going forward. So it's known back to the 80s by work of Johnson and Lindenstrauss that these embeddings exist with a number of rows in your matrix that scales only logarithmically in the cardinality of the set. And this distortion that you have for this bi-Lipschitz map is controlled by epsilon, and you have a 1 over epsilon squared scaling. So these are really useful linear embeddings of data sets, primarily because they're oblivious, which is sort of a terminology again from the computer science universe, meaning that with high probability random matrices will achieve these inequalities, and you don't really need to know any detailed information whatsoever about your finite set S, except for a cardinality bound, which is an incredibly convenient thing. So you can embed a data set without even knowing what it is in advance and just having some idea about how large it is. So there's been a lot of work since the 80s coming up with, again, bounds on M for different types of distributions on random matrices. So their Gaussian random matrices are probably the easiest and first example. You just have independent and identically distributed mean 0, variance 1 entries in a random matrix. Normalize it appropriately, and then you see that you can achieve this number of rows and still guarantee success. And there are also more structured types of random matrices that, for example, Dominic's advisor has done some work with involving, for example, subsampled Fourier ensembles. So, and once this type of example, you can do something like pick a random diagonal with plus minus ones on the diagonal. So that's the source of the randomness here. Take a discrete Fourier transform matrix F, and then just subsample a small number of the Fourier coefficients, the discrete Fourier coefficients, and get a matrix that again satisfies this with a few extra log factors. But now, because of all the nice structure we have here, now has fast matrix vector multiplies. So summarizing literally thousands of papers here, I think, in this slide. And then, of course, we've been talking about finite sets. So the next thing that people thought about and started utilizing in a bunch of different contexts in both applied mathematics and computer science literature were, similar embedding results for infinite sets. So maybe the easiest example would be to consider a subset S of Euclidean space, which is a subspace. So you make S a low-dimensional subspace and possibly consider it to be, for example, an eigenspace that, again, you don't need to know in advance. So if you want to compute something about the eigenspace of some very large matrix, you can compress the matrix, guarantee compression of the most important eigenspace that you might be interested in, and then do some interesting randomized numerical linear algebra using these types of embeddings. Another example where there was many papers published was if you took S to be sparse vectors, so all vectors that have at most S non-zero entries, and preserved all of the pairwise distances this way, and that gives you the restricted isometry property, and you have many papers about that in compressive sensing. Here I'm going to be, for a large portion of the talk, mostly interested in the case where our set S is a submanifold of high-dimensional Euclidean space, so a low-dimensional manifold, which is, again, a very common data model in data science and signal processing applications. So that's sort of how this fits into the broader theme of all of this embedding work. So more review here. Hopefully I'm not boring you too much, Dominic. If you have an infinite set, then you can't use cardinality bounds in order to describe how many rows you need. So you have to describe the complexity of your infinite set with some other type of quantity. So we'll be talking about the Gaussian width of a set here, of sets here. So all that is, you take a random vector with mean 0, variance 1 entries, look at the inner product between that vector and elements of your set S and take the supremum, and then take the expectation over your random vector G, and that gives you the Gaussian width of the set. So it can replace cardinality as a measure of set complexity from the previous slide. And some examples, so if S is a finite subset of the L2 ball, so none of the elements of your finite set are too large, then you can bound this Gaussian width by the square root of the cardinality and get results similar to what we described on the previous slide for sub-Gaussian random matrices, for example. If S is a unit L2 ball of a little d-dimensional subspace, then the Gaussian width looks like the square root of d. So it takes on the characteristics of the dimension of your subspace and sort of shows you that it's capturing, in some sense, how complex the subset is in that case. If you have S sparse vectors, then you can bound this as the square root of S times log d over S. So this is all S sparse vectors, and you get results that look like compressive sensing results here. And then there are some really nice theorems in, for example, Verschinen's high-dimensional probability book that tell you that sub-Gaussian matrix can again achieve this embedding property as long as you have the Gaussian width of the set over epsilon squared rows up to constants, which I'm neglecting. So you can extend all of these results to infinite sets and nice things happen. So here's a little bit more detail of the theorem. So you can indeed take your finite set, normalize it after excluding 0. So that's all this U is. We're just normalizing the things. Look at the Gaussian width, and the square of that quantity will tell you effectively what the dimension should be of your random matrix in order to achieve this nice preservation of pairwise distances with high probability. And then you can add a few more rows if you want to increase the probability that you succeed. And then there are, this is for sub-Gaussian random matrices. There are similar results for subsampled Fourier systems, again, with more structure, so they have fast matrix vector multiplies. by Oymak and some of his collaborators from several years ago that again end up depending on the Gaussian width of the set squared times additional log factors. So all of the sort of story about finite sets is sort of reproducible in the infinite set case if you follow along this sort of trajectory here. Okay, so all prior work, it's really nice. And it tells you a lot about sufficient bounds, so how big M should be in order to guarantee that this is going to work with high probability. You can ask about what's necessary, of course, and think about what the sort of embedding dimension has to be for any function to preserve the pairwise Euclidean distances in this way. So this is a result here by Jelani Nelson and the collaborator from several years ago. And effectively what it says is that there is a worst case set S of any cardinality that you happen to care about, such that any function, even a nonlinear function, which satisfies this sort of bi-Lipschitz embedding property, if you take square roots of everything, for all pairs of points in S preserving these pairwise distances, has to have an embedding dimension which is logarithmic in N for epsilon not too small over epsilon squared. So effectively what this tells you is that there is a worst case set that forces this same dimension that shows up in the upper bounds provided by random linear maps. And so in some sense, linear epsilon JL embeddings are optimal for epsilon not too small. So somewhat surprising. Nonlinear functions can't help you too much beyond what a random matrix will do for you in this regime of epsilon. So in general, you need to have, for finite sets, a logarithmic number of in the cardinality rows over epsilon squared. And now you can start asking some questions that right away. So you can ask yourself, how common are these sets? So this says there's a worst case set that forces you to do this. What if I have a particular set that I'm interested in embedding that isn't worst case because, for example, it has some geometric structure? What if I have an infinite set where this cardinality bound isn't terribly helpful? What can I say about that? What if epsilon is smaller than this cutoff, right? What happens then? So there are open questions here that are left open. So I thought about this a little bit with Ben Schmidt, who's a geometer at Michigan State University, and Arman Tevakoli, who's a graduate student of mine, and at least thought about proving something for infinite sets. So this is what we came up with. So let's suppose that we have a function f from S to Rm, could be nonlinear, any function that achieves this this pairwise distance preservation up to distortion epsilon, the way we've been talking about. Then M has to be larger than the Gaussian width of the set squared, divided by its diameter, and with some additional decorations involving epsilon. So you can show this for infinite sets, and then sort of realizing that there are finite sets that achieve this square root of log S dependence for Gaussian width. You see that you've, at least for large epsilon close to 1, you've generalized the previous result for finite sets. And it again shows that sub-Gaussian embedding result is that I mentioned from Verschinnen is near optimal, at least with respect to the scaling in the Gaussian width of the set. So you have this squared Gaussian width type scaling, and you sort of need it. So this is helpful because it's going to apply to any set S. So it's not just an existence result about one bad set. It tells you something about whatever set you actually care about. And if you pick that set to be sparse vectors, for example, with at most S non-zero entries, you can see that using nonlinear functions to try to achieve an RIP type property isn't going to help you very much. So again, you're going to need like S log n over S number of rows, even if you try to use a nonlinear function. And so random matrices, again, are somehow doing about as well as you can do for preserving infinite sets. So all of that said, the epsilon dependence here, you'll note, is not what you would expect. We would expect something like a 1 over epsilon squared to be appearing somewhere. That's not what we get here. So that's something that in general still needs to be fixed. And I'm not quite sure how to fix it. So if anyone's interested in thinking about something related to this stuff, there's an open problem for you. Okay, so having this result, for example, that holds for arbitrary sets S, we can now consider sets that have geometric structure, for example, manifolds, and try to come up with lower bounds that might match prior upper bounds by folks like Wakin and Rich Baranuk and other folks who have worked on upper bounds for embedding random matrices using random matrices to embed manifolds. So a few assumptions about what we're going to be working with here. So we're going to be considering manifolds that are compact subsets of RD. We're going to allow them to have boundary, which is going to generalize some of these prior results because they were sort of arguments that didn't allow the manifolds in question to have boundary. Something I want to point out. They should be sufficiently smooth. You're going to see that you want them to be little d dimensional, so quite a bit lower dimensional than the ambient Euclidean space that they're embedded in. And we're going to use the concept of reach to quantify how complicated or sort of wild their geometry is or not. So reach is this useful concept introduced by Federer in 1959. So for the students or other folks around who haven't thought about reach before or for a while, let's take a little detour and actually show you what reach is so that I can claim you've learned or been introduced to something concrete and potentially useful in this talk. All right, so anyways, let's talk about what reach is. So if I take a set M, could be a submanifold or any other subset of Euclidean space, and I can talk about a distance function to the set, right, defined using the infimum. So for any point X, I can look for the closest point in M and take the infimum of the Euclidean distances. And then the projective domain of M, what I'm going to mean by that is I just want to take all the points in RD, so the big Euclidean space, that have a unique nearest neighbor to the manifold. Okay, so there should be some unique entry on M that actually achieves this distance. So what I want to think about is, if you want to look at this picture, if my manifold is this little patch of plane here, I want the point X like this point, where if I grow a ball around them, the first time I touch the manifold, I touch it in one unique place. And if that happens, then it's in the projective domain. So there's a well-defined nearest neighbor projection for those points. Okay, so the manifold is always a subset of its projective domain. And for a point or a subspace, for example, you always have all of Euclidean space is going to have a unique nearest neighbor. So you're good with making the projective domain in the entire Euclidean space. All right, so seeing how this projective domain interacts with quantities of interest when you're talking about manifolds, you can take a look at examples like this. So if I take my set M to be a circle, so a one-dimensional circle in, well, two-dimensional space here, but scale it up if you like. And consider this example where I take these green points, which are going to be in the projective domain, and grow a little ball around them. They're going to touch this circle in one unique place when they first touch it. And so all of these green points are going to be in the projective domain of the circle. And in fact, if you look at this, everything's going to be in the projective domain of the circle except for the center. In the center, you have the problem where it touches the entire circle at the same time. So there's no unique nearest neighbor projection, right? So the projective domain of a sphere is going to be everything except for the center. for one-dimensional curves, if I have a one-dimensional curve here, you can see that areas that have greater amounts of curvature are going to produce smaller sort of constrained projective domain sets. So this red point is not in the projective domain because when I grow this ball around it in this curvy section of the line, it touches 2 points at the same time, and so it's not in the projective domain. But over here where I have a flatter portion of the curve, it's going to touch in one spot and be in the projective domain, right? So curvature is going to limit this projective domain. Okay, so back to reach. So what is reach? Well, it's going to be defined as the radius of the largest tube around the manifold that you can fit in the projective domain. So what is a tube? You take all the points that are distance r for a tube of radius r away from the manifold. That's the tube around the manifold. And then the reach is the largest domain so that the tube is a subset of the projective domain. So it's sort of the uniform distance you can walk away from the manifold in any part of the manifold and be guaranteed that you're still going to have a nearest neighbor, a unique nearest neighbor on the manifold. So all points within this distance of M are going to have a unique nearest neighbor. This is sort of a nice quantity in general. So if you want a little homework assignment to think about next time you're really bored or can't sleep or whatever, or right now if you're wishing that you weren't in this talk, you can prove things like, for example, that the reach of a set is equal to infinity if and only if it's a closed and convex set. So sort of a nice thing. So you can characterize different types of sets based on what their reach is. And more generally, the intuition is the larger the reach of a set is, the more simple, sort of flat, non-self-intersecting, the more like a plane, for example, this manifold is going to look. So big reach means simple geometry, for lack of a more specific statement that can be said quickly. All right, so a few more examples. The reach of a line segment then with the endpoints included, this is going to be have these tubes that look like pills expanding around the line segment. So here's an example of one of the tubes. And it's going to be infinity. This is a convex set line segment. So everything will have a unique nearest neighbor. You can sort of get a feeling of what it looks like by looking at the tubes. And the reach of a sphere is going to be the radius of a sphere, right? Because the center is not in it. So you get donuts, and the donuts start hitting each other in the center as soon as the reach gets to be as big as the radius of the sphere. All right, so some interesting properties of reach. All right, so now that we have some idea what reach is about, let's take a look at a prior result about embedding manifolds without boundary using random matrices. So this is a really nice theorem by Wakin and the student from several years ago. And it says, if M is a compact d-dimensional submanifold that satisfies this particular condition, when you take its reach to the dth power divided by d, it has this particular condition holding. Then, as long as you make M large enough, so larger than the dimension of the manifold times some additional log factors, you will achieve this embedding property, this sort of bi-Lipschitz embedding property that you want with a random matrix with high probability, 1 minus p, and you can make that probability as close to 1 as you want by adjusting the number of rows you use. So nice result. Really like it a lot. There are a couple things that you can think about with respect to it, though. So this condition that it requires to hold, they mentioned in the paper actually is technically not necessary. So you can think about why is it there and what effect does it have? Can you remove it? And what happens if you remove it? And manifolds with boundary aren't sort of included in this argument. So you can ask how can you generalize this to include manifolds with boundary, and how optimal is this result for manifolds without boundary? So several questions that you can ask here. So related to these lower bounds that we saw for infinite sets, you can work on producing necessary conditions for any function f, potentially nonlinear even, to preserve all the pairwise distances in a manifold by using this infinite set lower bound that we had talked about before. So again, this is work with Ben Schmidt and Armand. And there are sort of two pieces to this result here. So it says, if you have a function, any function that embeds a d-dimensional submanifold of M into m-dimensional space, Euclidean space, then there are sort of two regimes. One regime is the regime where reach is larger than this particular cutoff, which sort of falls out of the analysis. Large reach means simple, flat, potentially subspace like manifolds, for example. You can think of it that way. Then you need a number of rows that scales like the dimension of the manifold, decorated with the diameter of the manifold has to be bigger than this, and some other factor here that involves the volume of the manifold divided by the volume of a d-dimensional Euclidean unit ball. So how large are you compared to a d-dimensional Euclidean unit ball? So you must have more rows than this. Okay. Otherwise, if you're in the small crazy reach regime, so small reach means you could be curving really quickly in some places, or possibly almost bending back and sort of having a near intersection, something like that. You need a number of rows that scales like this. So you have a log factor involving the volume. You have the dimension again, but you now have this additional reach squared over diameter squared type of condition that appears in your lower bound. So it turns out that the small reach case is the one that's compatible with Mike Wakin and his students' result. So their condition was this. This is our condition. If you rearrange things, you'll see that there is an overlapping. This is where the conditions overlap. And if you go back and look at the upper bound that they have and this lower bound for M, you see that they're off by at most reach squared over the diameter of M squared. And this is for any arbitrary nonlinear function. So in some sense, this is the most that they're embedding using a random matrix is loose by this sort of factor. So sort of the general take home message is, again, that allowing F to be nonlinear doesn't seem to help as dramatically as you might think it would in terms of reducing the dimension that you can achieve embedding something like this. Which is sort of surprising. So random matrices and Wakin's result is pretty close to tight and seems to work quite well for embedding manifolds compared to even nonlinear competition.
Sorry, can I ask something?
Yes.
Can you go back to the slide with the two regimes, please?
Yes.
Yeah. So I'm not sure if this is weird or not, but is it clear I mean, intuitively, you would expect that the regime where the manifold is complicated would require a higher embedding dimension, right?
Yeah, that is a little weird. I think what you're seeing here is that our proof techniques aren't strong enough to capture all the complexity that can happen in that situation.
Oh, so this is basically quite far from being sharp in any sense.
I don't think that this is even sharp exactly. So
okay.
in other words, that also leads me even more to suspect that Wakin's result is actually pretty good, because I don't know if this is really needed or not, and I suspect it probably isn't, because just like you say, when the manifold gets complicated, it's like the lower bound gives up and says, I don't know what's going on, you have to have this number of rows, but I can't tell you anything better than that. And there's probably much better things that you could say. For example, I mean, I guess there are better things you could say. So if you have a manifold that's very, very smooth in some spot and then does something crazy over here, then there will be a regime where this bound holds and the other one holds in the other regime. If you look at it as sort of a union of two manifolds or look at them separately. And so there's definitely interplay there that's in which this is weak and not quite optimal. So it's definitely improvement here. If it looks like something that anyone is interested in, there is improvements that could be made, I'm sure. Yes, so that's any other questions or anything since we, there's a bird flying behind me. That's interesting. Anyway, so one other thing we worked on, sorry for the wall of text here, but we also wanted to generalize this nice result by Wakin and the student to include manifolds with boundary. So just a little bit about this, we're allowing the manifold to have boundary, and now we're taking the reach of the original manifold and its volume, as well as the enumerating the components of the boundary and looking at their reaches. We take the minimum one, so sort of the craziest piece. You could break it up in other ways if you wanted, and the volume of the boundary, and then you can create this quantity alpha m and then beta m, which comes directly from it, which involves what you would expect. It's sort of this composite reach of the boundary elements and the original manifold, the dimension, and the volumes of the boundary and the original manifold. Weighted with this Euclidean ball volume here. And then you can say that if you have a number of rows that's larger than the square root of the log of this beta component, you'll have a random matrix that with high probability, a sub-Gaussian random matrix will achieve this bi-Lipschitz embedding condition that you want. Again, right? And all you need to know here is some bound on this reach parameter and something about the volume. So you don't have any detailed information about the manifold whatsoever, just some sort of upper bound on these geometric quantities. So this oblivious nature of these randomized embeddings is still there and working for you, which is interesting, I think. All right.
Can I ask a question?
Yes, please.
So, I mean, you also could do in some sense if you have a manifold, right? You just compute its Gaussian width or so, and basically you could try to compare this result with the one by Verschienen, right? Can you say something about that?
That's more or less how you get this. So, computing the Gaussian width of a manifold with boundary is the difficult part of the work here, and then you can combine it with Verschienen's result. So we'll talk about that in the proof, but effectively what we spent a lot of time doing in proving this result was coming up with a good Gaussian width bound for an arbitrary manifold with boundary, and figured out that this is what the Gaussian width bound ends up depending on, or can depend on. So yeah, that is a proof path that we went on. And as well as proving results for structured random matrices. So that was for sub-Gaussian random matrices. You can get similar results for matrices with fast matrix vector multiplies, including things that are faster than d log d, which is what this would traditionally be. You can actually get it down to d log m, the embedding dimension. Matrix vector multiplies are very structured matrices that have the same type of embedding dimension plus some additional log factors, right? So, and the proof, as I knew Dominic would know, is effectively going to be you coming up with using epsilon JL-Embedding bounds in terms of Gaussian width, either from Verschienen or some that you prove yourself for these structured type of matrix ensembles with these fast matrix vector multiplies, and then combining it with estimates for the Gaussian width of unit secants of a manifold. So what does that mean? So the result that we had there is really about estimating the Gaussian, as well as Wakin's sort of hidden down in the guts. It's really about estimating the Gaussian width of this what I'll call unit secant set for a manifold, right? So you take all pairwise or all pairs of points in the manifold, look at their differences and normalize them. You can then take the closure, and this is just a compact subset of RD. And so you can now work with getting covering bounds for this set, right? As X gets close to Y, you have the tangent bundles sort of popping out when you have a manifold assumption. So the geometry comes in that sort of situation. You get covering number bounds for this set, and then you use those to estimate the Gaussian width of the set by sort of standard techniques, let's say. Dudley's inequality, etc. Your favorite chaining argument. Yep, exactly. So the covering number bounds for the lower bounds, you do something similar actually. And so you really need upper and lower bounds for packings and coverings of a manifold. And they end up looking like this. So you really want to know how much volume of the manifold a ball centered at a point of the manifold can capture. So sort of a strange thing, and you want to know the maximum and the infimum that you can capture of a manifold when you sort of put a ball on it. And this requires you to consider a lot of detailed geometry of M as well as boundary effects. Here's sort of a related picture, right? So I want to take a point on the manifold, I put a ball around it, and then I'm interested in the amount of volume that's captured in this intersection. And that's what I sort of need in order to estimate my covering numbers. So that means you have to consider worst case behavior of the manifold in order to have as much or as little possible area captured, depending on which inequality you're proving. And you sort of handle that by saying that there's a geodesic ball around this point in the manifold contained inside of this Euclidean ball. And then there are comparison theorems which let you compare the volume of a geodesic ball in a manifold to sort of worst case model spaces like spheres, sort of constant curvature model spaces, and bound the volume that can be captured in the manifold given that you have upper and lower bounds on its curvature information using exactly using the reach condition that you've assumed. So you push all of this through, take some time, and you're able to get it all worked out in a nice rigorous way. Some of the issues with boundary effects that you have to consider. So maybe the easiest one to understand is if you have a point close to the boundary and you want to know how much area is captured by a ball around the boundary, clearly the geometry of the boundary comes into play. So here, this blue area is real area that we have to count, upper and lower bound, and the white stuff outside of the boundary is fake, and we have to account for that and not mess up our bounds because of this. So you have to sort of treat the boundary separately, and that's why it appears separately in our theorems. And in working with the geometric results you end up using, it becomes obnoxious that geodesics are not all C2 and they're not unique. So if I start at A and start following a geodesic in this direction, as soon as I hit the boundary, it can bifurcate. And I could either end up at B or follow the boundary and end up at C, or maybe hit another boundary and end up at D. So if you are using any result that requires you to have a unique geodesic somewhere, you have problems anytime you're too close to the boundary. All right, great. We have talked a lot in the last few slides about using random matrices to embed manifolds with or without boundary, coming up with lower bounds to see that using random matrices or linear embedding seems to work about as well, maybe, as any nonlinear embedding that you could use. Let's turn a little bit now to some terminal embedding of a set definition here, which is an extension of a Johnson-Lindenstrauss embedding proposed in the computer science community several years ago. So what is a terminal embedding of a set? Same thing. We're going to have a function f that we want to use to embed a set, preserve all the pairwise distances in the set, and sort of most interestingly, we actually want to allow ourselves to also preserve all distances from anywhere in the ambient space where the set is sitting to the set. So the important thing to look at here to see the difference between this and a JL embedding is the red portion here involving V. We do not just preserve all of the distances between points in S, which we do. We also do that, but we also have to preserve all the distances of outside points to S with this function. Okay, so right away, looking at that sort of creepily strengthened property, you see that a linear embedding F is never going to work. We'll never have this property if you have any compression whatsoever, if M is less than D. And you can just set your V equal to any U in the set plus something in the null space, and you will violate this condition right away. So nothing linear is going to work. And so nothing we know about random matrices or high dimensional probability that we're used to using is going to help us here. Well, that's not actually true. It's going to help us a lot, but not obviously going to help us here from the get-go. Nonetheless, Jelani Nelson and one of his students has shown that these exist for finite sets with on the order of the same dimension as a Johnson-Lindenstrauss embedding. So you can actually do this. You just need log of the cardinality of any finite set and the same sort of distortion performance, and you can build one of these functions and preserve all of these distances, just in the lower dimensional space, right? Even though you're measuring distances from things that aren't in the set, anything not in the set. It's kind of a little wild. I think the first time I saw it, I was quite interested in this. So if you just restrict the domain of this thing, it's going to be bi-Lipschitz on S. And so this M is certainly optimal, right? You couldn't improve this without doing better than a Johnson-Lindenstrauss map. So this is really good for finite sets. One thing you do lose is in order to correctly map points that are not in S, you have to actually know what S is in detail. So the oblivious nature of these functions is gone. We can't use a random matrix that doesn't care what the set is anymore. We have to actually know what the set is in order to correctly map points not in the set so that they preserve all distances to everything in the set. So the obliviousness is going to be gone. So you do lose something. Okay, so how can you possibly compute one of these things? So this is a method that my graduate student Mark Roach and I have used. That's sort of a modification of something suggested by Jelani Nelson. And let's take a look at how this works. So what we're going to do is build off of an epsilon Johnson-Lindenstrauss map. So that embeds the original set we care about. So let's take a random matrix with Gaussian entries, for example, something that we want to behave like a standard Johnson-Lindenstrauss embedding of our set S. Okay, so I'm going to use this guy. That's what pi is. And I want to now evaluate my function f at some point u, which is not in S, let's say, in a way that preserves in the embedded space all of the distances from u to everything in S correctly, up to this epsilon distortion anyways. Okay, so what do? Well, I compute the nearest neighbor to this point in S. So I can do this, here's X nearest neighbor, right? Now you see I need to know S in order to correctly find the nearest neighbor, or even approximately find one. So I need to know S. Then what I'm going to do is find a minimizer of this objective function. This is with a variable z, right? U and X nearest neighbor. These are both parameters now that are fixed because I know what I'm trying to embed. Z is my variable. that I'm trying to come up with a minimizer for in the embedded space. And I just want Z to have a 2 norm that's less than the distance between U and its nearest neighbor. And I want Z in the embedded space to approximately preserve all of the inner products between the vector from the point I'm trying to embed near and its nearest neighbor, the inner product of that sort of difference vector with all of the other vectors between everything in S and this nearest neighbor. So I want to try to somehow preserve all of the inner product information, at least approximately, for everything in the set. Whoops. So that's what I'm doing. And then how do I actually compute the embedding? Well, if I have something in S, I'm just going to Johnson-Lindenstrauss it because I know that works. This is, I'm assuming effectively that this is a Johnson-Lindenstrauss embedding. And if I don't, I'm going to embed its nearest neighbor and then fix it up with this minimizer in the first M coordinates. And then I'll add in one additional coordinate at the end that involves the difference in norm between my minimizer U prime and this vector difference between U and XN, the nearest neighbor to U. In fact, if you stay close to S, a finite set S sufficiently close, this reduces to this. So it's not quite so mysterious what's going on here. Let's imagine that U is in S and we embed it. Then the nearest neighbor of U and S is going to be U. So X nearest neighbor is going to be equal to U, right? If U is in S. And that means that this constraint is going to force Z to be 0 because this distance will be 0 if U is its own nearest neighbor. So Z is going to have to be 0. There won't be any other minimizer that will satisfy the constraints. And so U prime is going to have to be 0. That's the only minimizer. So this will be 0. This is 0. This is 0. And the nearest neighbor is U. So it actually reduces down to the original JL embedding. If you have something really close to the set S, you're basically doing a Johnson-Lindenstrauss embedding at that point, right? Not modifying it much. So
is it clear that there's always a set which satisfies the constraints?
Yes, that is the entire proof of the following theorem.
Oh, sorry.
Yeah, so, well, that's the entire proof of let's say that's the entire proof of this theorem, more or less. Not the entire proof, but important part 1 of the proof is there is always a solution that satisfies these constraints. They don't even care about an objective function. They just want anything that satisfies the constraints. So it's really more of a constraint satisfaction problem. And then they show that anything that satisfies those constraints will allow you to get this type of embedding. So that's sort of important part 2. It's a 2-part proof. So in practice, however, which I'll sort of discuss next, this objective function seems to work well in practice for nearest neighbor classification problems in a reduced space. So I don't know how much time I have left, but I can talk about that next. Yes, so let's sort of justify why my graduate student thought this was a good objective function to slap in here to solve these types of problems. So let's just set up a compressive nearest neighbor classification example. So I'm going to pick a training set, subset of some labeled data, MNIST. I'm thinking of, this is going to be one of our examples, not surprising to anyone here, I'm sure. Choose a disjoint test set, right? What we're going to do is embed the training data with a function f. So we know it in its labels. We can embed it into a low dimensional Euclidean space, reducing the dimension as much as possible. And then we can compute the embeddings of all the test data. And these terminal embeddings will guarantee that all of these guys are, all of their distances to all of the training data is approximately preserved, because that's what the property does for us, even though, right, we didn't know them in advance. And then I'm going to do nearest neighbor classification on the embedded test data in this low dimensional Euclidean space. So standard sort of compressive nearest neighbor classification. All the pairwise Euclidean distances are preserved, so this should probably work pretty well, hopefully. And indeed it does. So a little bit of a busy slide, but Here, let's us focus on figure A and figure C. These are the sort of classification results I'm interested in. This is MNIST data that I'm using here. This is coil 100. So there are 100 different objects. You need to pick which of the 100 objects you're looking at based on having different rotations of the 100 objects for your training data. So that's what this is. We vectorize the images. And so here what you're seeing is this dotted black line is no compression whatsoever. So I'm just using the raw MNIST data to do nearest neighbor classification without compressing anything, right? And this red line is a terminal embedding computed by the prior slide. And what you see is, despite the fact that the original data is 784 dimensional, like after vectorization, once you get to 24 or 26 dimensions, you effectively have less than 1% difference in the nearest neighbor classification result. So this terminal embedding zeroes right in on doing as well as you do with no compression whatsoever. And here, I mean, going from 784 to 24 is massive amounts of, dimensionality reduction that we're doing here. Similar behavior with coil. Again, terminal embedding. This line is no embedding whatsoever, just using the raw data, uncompressed to do nearest neighbor classification. You quickly reach the same sort of classification accuracies, and here M is only 15, and the original vectorized images are 16,384. So you're really seeing that in some sense this coil data set is only 15 dimensional, despite the fact that the images upon vectorization are quite massive, right? So these other things, these are linear Johnson-Lindenstrauss embeddings. These are Gaussian random matrices that you use, and you just use that as your embedding, hoping that it works. And it does sort of work, but there's a 10% difference here, right, between the accuracies you get with a standard random matrix and one of these terminal embeddings. So these highly nonlinear embeddings are pushing the classes further apart somehow and providing value in these classification experiments. So they seem to work pretty well in practice. You can also ask the same types of questions we did before. So do they work for infinite sets? And the answer is yes. So there's going to be a map that embeds an infinite set that satisfies this exact type of maybe what you would expect bound on M, involving the Gaussian width of the unit secants of the set over epsilon squared. And then you preserve all the pairwise distances between the points in the infinite set M, as well as all distances from any other point in Euclidean space to M, right? Same sort of generalization that you had before. You can actually compute a function like this using an algorithm similar to what we were using to do those nearest neighbor classification embeddings, but you need to have quite a dense cover of the unit secants of your infinite set. So you can do it, but it gets computationally difficult quickly, as you can imagine, because you have to solve that minimization problem. And the number of constraints you have is equal to the size of the cover you need. So gets computationally tricky, but theoretically, there's nothing stopping you, and it works in about the same way as what that slide sort of implied. You take a linear Johnson-Lindenstrauss map that preserves all the pairwise distances, so just a matrix like we had before, and you cook up a nonlinear function in a fairly similar way that takes all the tubes around the original manifold, right, and embeds them to tubes around the embedded manifold in sort of a compressive way. So you preserve M, and all the tubes around M you map to smushed tubes of similar radius around your embedded M, and then everything works out. and you get theorems like this in the manifold setting. So you can preserve the distances between all pairs of points in the manifold, as well as all points in the ambient space to the manifold, with a dimension for your embedding function, your nonlinear embedding function, that satisfies a very similar looking type of bound to what we had for the linear Johnson-Lindenstrauss case, because it really is, you're using that as your initial map, and then you're doing this outer bi-Lipschitz extension in order to get this more complicated nonlinear function that has this stronger property. Okay, so rushing a little bit here. By the way, just tell me if I should stop, because I could stop now, or I could do 3 more slides.
You're pretty much at the end of the time now, so.
Okay, that's fine. All right, great. So I will just stop it here and mention that maybe very quickly, you can show that you can do better than sort of established compressive sensing theory for linear maps. You can get best S term approximation guarantees using these nonlinear maps with respect to the 2 norm, which is something that has been shown that you can't do in compressive sensing if you have linear measurements. So these nonlinear functions that have this additional strength actually do give you sort of theoretical power that you didn't have with linear maps. But so I'll just leave it at that. And thank you all very much for listening to me talk for so long. And here are some papers you can look at if you're at all interested in this stuff.
Okay, Mark, thanks for a nice talk. So are there any questions